Hello, everybody. Welcome to another session of MEC 392, the manufacturing processes. Today, we'll talk about another way of making things, which is powder metallurgy. So far, we've learned different ways to work with metal. When it is a sheet, we know sheet metal working is the process to go. Machining is another way to remove materials and get the desired shape. Last week, we learned casting. In casting, we melt a metal and we pour it into a cavity. And we learned there are different ways to do casting, in particular sand casting, where our mold is made out of sand. Die casting, which is very similar to injection molding, plastic injection molding. And you've learned there are two methods, cold and hot chamber. And also you learn investment or lost wax casting. Today, the process to make an object out of a metal is a little bit different than previous approach. Instead of melting a metal, we make a powder out of it and we make the desired part that we want. All right, so this is the topic for our today discussion and today lecture. It's a relatively simpler and shorter topic and similar to previous lecture. Please feel free to ask question at any point. Again, as I said before, I don't check the chat. So if you have a question, that's okay. Just unmute yourself and interrupt me. All right, so let's get started, but before I start, is there any question or concern or anything that either related or non-related to this topic you want to say? Okay, I take it as a no. So let's delve into it. I guess I need to maybe move my camera a little bit here, right? Okay, so a simple definition of powder metallurgy, as I said here, is a process which we will, first of all, we work with powder. We compress powder into a desired shape, all right? And then we heat it, but we don't melt the powder. We heat it, and there is a process which we call it sintering. It's just different terminology which you need to know. When we say a sinter part, or let me write it here. When something is being sintered, we say is equal to say heated without melting. So in casting, you saw we have to melt a metal. So when we use the terminology sintering, it means we don't melt a metal. It is slightly melt, maybe in outer layer, which I will elaborate on that shortly. And we get the object that we want out of this method. So this method first was used in 1900, so about 120 years ago, to make the filament for basically bulb, like the tungsten filament. This basically wire or filament. So and this one is tungsten filament. In particular, because tungsten has a very, very high melting temperature. If you recall from the very first or second lectures, it's one of those refractory material which has a very high melting points. And making a wire or filament so thin out of it with other approach is not easy. So in 1900, it was the first use of this approach to make like this part. Another things that you may think of is if you're using a pen, which the pen, maybe I have one here with me, like a pen, a regular pen, which has one of those ball points. that tiny ball points, think of any other approach to make those tiny balls. For example, casting maybe is not a good way to make those, right? And machining, of course not, to make such a small sphere. So powder metallurgy is a common way to make those ball for the ballpoint pen. Okay, so if we want to say the main basically application of powder metallurgy, so in terms of metals, so in industry, iron, steel, and aluminum are the main, we can say, users of this process. Copper, nickel, and also, as I said, refractory metals, which has a very high melting point, such as titanium and tungsten also are materials that frequently people use this approach to make things out of this material. So to make stuff by powder metallurgy, they can be very, very small, like a few millimeters, and even smaller. The ball of a ballpoint pen the diameter is 1 millimeter, right? So to large parts, like 50 centimeters or maybe even bigger. However, it's not recommended. So suggestion is not going further than 2.5 kilogram. And again, it's just a suggestion. People have made larger part with powder metallurgy, like heavier part. And the main reason is after you compress a part, if the part is too large or too heavy, first of all, compacting them maybe is not uniform. The outer layer is under higher pressure. As it gets to inner core, there is less pressure and less compaction, which is not in our favor. And secondly, when we put it in an oven for sintering, maybe the outer layer gets melted, but the inner layer still is just in a form of powder. So we try to keep it for smaller parts, usually this method. So a few examples, as you saw in this picture, gears, rings, many parts for car, and like connecting rods, as I pointed out here, like the piston rings for cars, and gears. One approach to make gears is powder metallurgy. Of course, people use different methods such as machining, like CNC machining, but making gears out of with powder metallurgy is very common. Cams, bushing, and bearing. In terms of bearing, we can make bearings that are self-lubricated or oil impregnated with this approach. So I will write down here then the type of bearing we mean here is self-lubricated. And when we say self-lubricated is they have this oily texture or oily basically surface, because the porosity of this approach make it possible to use oil and make it oily, like a oily basically material. Cutting tools, you can think of like a lathe cutting tool which made out of tungsten. Tungsten have a very, very high melting temperature. Can you imagine making a tungsten out of casting? Of course, melting it possible, but then you need to cast it into a mold, right? So the mold has to be made out of a material which has a even very higher temperature, which is, again, making that is not impossible, but it's very difficult. So, but using powder metallurgy make it possible. So cutting tools is very common to use this approach. And surgical implants, this is a very common approach. Many implants made out of titanium, and this approach is very common. Surgical tools as well, like the tools that people use for doing surgery. And magnet. So to make magnet, then powder metallurgy, magnet of different shape, powder metallurgy is a common approach. As you can see, there is a large application for this approach. And this approach considered to be relatively a new approach. As you saw, first was used in 1900, but it was until recently, by recently I mean 30 or 40 years ago, which it becomes popular. There are evidence, which is more like history, that people found some tools from 5,000 years ago, somewhere in Egypt, that they sort of speculate that the parts were made by powder metallurgy. Maybe at that time somehow they found a way to make powder out of a metal, and then they compact it into something and they put it into an, not oven, in a fire or something, and in furnace or something, and they made a part. But it's considered to be relatively a new manufacturing process. So a few examples here, as you can see in these pictures. Again, car connecting rod. And the picture on the right is for clutches, the part that in a car clutches. Again, is very common to use powder metallurgy. Another example is the stator core of an electric motor, which is a magnetic, usually material, and powder metallurgy is a way to make it. And on the right here, it's again a core for a rotor in a hydraulic electric motors made by powder metallurgy. I guess in one of those earlier videos, probably you watch, hopefully you watch, it shows many applications of powder metallurgy. I believe it was one of those videos which you had to watch for your start quiz. And here as well, you can see powder metallurgy can find many applications. But why it is so popular? Well, these are few reasons that I pointed out here. However, this list can go for more also benefits of using powder metallurgy. First of all, it's zero waste. You can think of making, let's say, a gear out of, let's say by CNC, you want to make a gear. So you need to machine it, right? You need to remove a lot of material out of it. And so then you realize you're going to waste a lot of material. So if you can make by machining, and you can use powder metallurgy. So it's obvious that the powder metallurgy, less waste, right? So more material saving. The second reason is we can eliminate the post-processing. Sometimes the approach that we decide to make something requires doing extra process on it. With powder metallurgy, we can claim that the shape we get is very close to our design. So maybe we need not too much post-process. Of course, with machining, we don't need post-process, but let's say with casting, sometimes we need to do extra process to machine the surface. And this one also results in more saving. The porous metal, which I will talk about it a little bit later, or something we call it oil impregnated. As I said, we can make a part which has this oily texture to it, and we can use it for self-lubricated bearing. And powder metallurgy is maybe the only way to make such a material or such a part. And the reason is because we make a part with powder, and there is porosity, like space between each of these particles of like the powder particles, which we can fill those spaces with oil, and we make, let's say, oil impregnated part. What else we can say? As I said, the high melting temperature, such as tungsten. Well, as I said, melting it and casting it is possible, but super expensive, right? And you know why. But if somehow we manage to make it in a form of powder, then we can compress it to a shape that we want easily, and then we just put it into a furnace to sinter it. And we don't need to melt it, basically. What else? We can say we can have a part made out of different like metals. Well, you may say it's also possible to do it with casting. That's true. However, let's say you want to make something, just make it up. Let's say you want to make something which made out of titanium and gold, right? Then how do you want to cast these things? Titanium melting temperature over 2000, but gold is just 200 C. So if you melt it to 2000, even if you melt them separately and pour them together, that high temperature is going to burn the lower temperature metal, right? And it's going to basically damage the property of the lower temperature metal. But with powder, you can easily mix, let's say, gold and titanium. You mix it because they are in form of powder. And later when you sinter it, of course, you make sure to sinter it to the temperature, considering the lower temperature one, to create the bonding. And again, it was a crazy example, but it's not unpopular because sometimes there are these parts for a specific application, even for implants, which at the same time that you want a high strength using, like, let's say titanium, you need also a good electrical conductivity or a good heat transfer, which you may use copper or gold. So you use that lower temperature, or let's say copper or gold, for a property of, let's say, heat transfer and electrical, also conductivity, but you use titanium for like strength. And it's possible to get a tolerance of 0.1 millimeter, which is very impressive, in one shot without any extra basically process, as I said. And the process can be automated. So it's one of those processes which you can have an automated machine, and hopefully you watch again one of those videos that I posted earlier, which the whole process can be automated, from compression to sending it to a furnace for sintering. So this is all good stuff. And of course, in this world, always we are not dealing with things that they are absolute good. What's bad about powder metallurgy? Can you guys think of any maybe cons of this process? Any negative aspect of this process? So again,
initial cost of the mold.
Initial cost of the mold. But think of it that if you want to make the same part with casting, you still had to make, Philip, the mold, right?
It's cost.
So in what aspect?
Possibly the materials part, because I assume for casting you can just use any melted material, whereas for powder you have to pre-process it to be a particular powder with a particular size and other constraints.
Yep, that's, as Jesse pointed out, it makes sense. So cost is one thing because you need to make powder, right? However, one may say, well, even for other approach, you need to melt the metal. So maybe the same amount of work required to melt a metal, it requires to make powder out of it. So, but cost can be one issue. However, it is something that can compete with other approach in that sense. What else you can think of? Try to think of that now you have like powder. You can compress it and sinter it, right? Probably you need less energy because sintering, you don't need to melt it, right? So which is all good things. But what can be wrong about this process? It cannot be all good. There must be something also bad about it. This is the way this world works, right? Always when there is something good, there is also some sort of drawback or some negative aspect somewhere.
Are the parts weaker?
Sorry, say it again.
Are the parts weaker when you make it using this method?
Well, no, because they claim that after doing a test, the part can be, they are not, let's say, as strong as forging. Forging on Thursday, you will see why it is stronger, but it can compete with casting.
It has uneven density and probably the material properties change throughout the material.
But Ahmad, we can say because it's powder, it's uniform, right? The density can be, and the property can be uniform everywhere because it's just tiny, tiny particles and it's uniform everywhere. Unless we make bulky, let's say, part which we cannot sinter the middle core. To give you a hint, think of powder. Do you think it's easier to storage and handle powder or just a solid piece of metal? Which one is easier?
Solids?
Solids, right? I'm not sure if you had experience making bread. So with flour, even if you are very careful, still it's going to be a spillage, right? Here and there, your hands is going to be floury and powdery, right? So then the first bad things about it, it's handling and storage of powder. Let me write it down here. Handling.
Can I just say something? I was actually just wondering that, isn't that a positive point in the sense that it takes less volume to store powder compared to any object that has a shape?
It is less volume. However, you need to build a container for it, right? Imagine like a big piece of solid metal, you can just leave it at the corner of a shop. But when you have powder, you need to build a container. You need to make sure that this container is not become contaminated, or let's say humidity or other things not getting into it. And now imagine when you order a powder from another company to come to your factory, they are going to probably charge you maybe 5 times more because they need a special car, a special container to put, or maybe special boxes to carry this powder. So the amount of, you're right, they maybe need less space. However, the saving from it is compared with handling and storage it's not significant. So handling and storage is expensive. And another bad thing is some metals, when they are in a form of powder, they can be explosive. So some powders can be explosive. So a good example, believe it or not, I didn't know it myself until a few years ago, when that was a different explosion. It was for a sawdust explosion in a sawmill. But at that time when I started studying the like the possibility of exploding, and I realized powder can be explosive because these tiny particles, even with aluminum, it can be explosive. And then when I study different metals, I realized metals can be explosive. So aluminum, magnesium, titanium, also zirconium, they can be explosive. Maybe there are other metals which you can look them up. When they are in the form of powder, they can be explosive. And now you can think of, if they are explosive, then even the storage and handling of it can be more and more expensive, right? That's the main drawback that people try to avoid powder metallurgy. And of course, these things draw the cost high.
Excuse me, I have a question.
Yes, please, go ahead, Panis.
What makes them explosive?
So with any particles, when we say the ratio of the outer surface, let's say consider a particle in the form of a sphere. The area, the surface compared with the volume is very large. So it makes it explosive because they can ignite very fast. And when they are in a form of powder, if they are in a, let's say in an enclosure, they can explode basically. However, in terms of what can ignite the fire, let's say with aluminum powder, I'm not exactly sure. Maybe that's it's easier for when they are in a form of powder to combine with oxygen and start a fire. But that's a good question. Maybe you can look it up to make sure.
Yeah.
Yeah. But you can think of when the smaller the form of these powders is, there is a higher, let's say, probability to start combining with oxygen, and then a little ignition, they can start a fire. All right.
So would they act as a fuel for the fire?
Of course, to start the fire, maybe at the beginning there is something, but when so and don't confuse it. I say fire, but it's more like the explosion that happens because they're in the form of powder, right? Yeah, maybe you cannot see a fire, but then big explosion.
Got it.
Right. I'll try to see if I can find something. Maybe next lecture I'll show you like when we have in material in form of powder, like this explosion is something that we need to be careful.
Excuse me, shouldn't we say also size is like limiting? In this case, it would be a bad thing.
The size, what do you mean? The size of the part?
Yes.
Of course, they are, thanks Kutan. So with powder metallurgy, we limited with smaller parts. However, let's say when we are making a part which the size is in a range that we want, maybe this is a choice to go with. So again, this is not a bad process. You see, there is all this benefit. However, we need to consider there are negative aspects to it as well. So let's see how this process works. Of course, we need to start with powder. We need to make powder, right? So this is like this schematic as it shows. This is one very common approach to make powder. You melt metal, you pour it into a funnel, and then you have, you can think of high pressure water. You spray it with water, and then the result is going to be very, very fast solidification of these small particles. So this process also, it's known as atomization. So let me write it down. Atomization. So if you heard of it somewhere, or the process of making powder, or powder process simply. All right. So you melt the metal, you pour it into a funnel or maybe a small orifice, and then you have high pressure water. Sometimes instead of water, people use air. So it's not always water. So air also sometimes air or gas. And it depends again on the application. It might be a particular gas. But water is the most common way. So another maybe approach that you should know is, let me draw it somewhere around here. People use a turning table. Let's say this is a cross section of the table. Imagine this is a table, the cross section. And this table, let's say, is rotating. And rotation is usually high, range of like 15 to 20,000 RPM. And then what we do is we have like at the top, let's say over here, there is maybe a funnel nozzle or something like that, which you pour like melting metal. Let me see, I use a better color so we don't mix it. Okay, we have here melting metal and it is going there. So my drawing not bad, right? Melting or molten metal. Somebody was supposed to tell me the difference between melted and molten. If anybody figure out the difference?
It's the same thing.
Same things? Well,
Yes, molten is for metals, melted is for everything else.
for cheese, right?
Yes.
That's correct. So you use melted cheese, you eat melted cheese, but you use molten, let's say, aluminum to make a part. When you melted a metal, it becomes molten. So molten metal, we pour it there, and this table is rotating very fast. When it hits the table, then we are hoping the result will be tiny, tiny particles throwing outside, and so we'll make the basically the powder. So there are things which can affect the shape and size of the powder. And so I write it down here, size and shape of powder depends on, you can guess. So of course, it depends on the temperature of molten metal. It depends on the rate that we pour it down. So let me add it down here. So one thing before we forget is the temperature of molten metal. So the second is rate of flow. How fast we pour it, the nozzle size, or the size of the orifice, tiny, big, and also we can say the water jet characteristic. Like it's how fast the speed of this water, the spray, the method that people use can make a difference. So because we can have like powder or these particles, the particles can be like nice and clean and a sphere shape, or they can be a needle sort of long shape like this one. And again, depends on the application that we want. We can decide what shape we can go for. All right. So let's now that we have the powder, let's see how this process works. Probably if you watch the videos, you saw it start with blending or mixing the powder. And you need this step if you are making something which needs two different powder together. All right. Ideally, we want these two powder to be like in the same melting point. However, as I said at the beginning, it's possible to combine metals which has different melting points, like significantly different melting points. The size, we can again decide what we want for the property. We mix the powder, then we add oil to this powder. It's just a regular oil. So can you think of why we add oil? The reason we add, like we do this step.
To help it stick together.
But oil, I believe, is gonna make it to separate more, right?
To remove it from the mold after.
You can think of that to remove it from mold. However, the surface are usually like a smooth, but that can be also a good reason. Make it easier to remove it from mold.
I think so. It can be more like a fluid. So when they're pressurizing it, it compresses easily.
That's right. So as Ahmad pointed out, we add oil to make it more we want the powder to flow easier when it goes to, let's say, thinner wall or complex geometry. Okay, so we add oil for a better flow of powder, better flow of powder into the mold. And then the next step is compression. We press them into the shape that we want. And then lastly, we do the sintering. Sintering, remember, it's another name people uses, as I write it down here. Oh, not that one, is fusion. And fusion, like in outer layers, when like as we saw here in this basically image, these particles, they fuse together. And again, when we do sintering for each particle, we don't melt it. So only, let's say, this sphere, this particle, the outer surface becomes melted, and so they, when they solidify, they bound together. So, and this picture shows the process, right? This green is the powder, and then we have the punch coming down, compress them, and then we eject it. With the part that we get is going to be very fragile. So this part, very fragile. So people compare it with like aspirin or tablets, so you can break it that easily by hand. And it is just strong enough to be sent to a furnace for sintering. I have a video here, maybe demonstrates. That's the same one that I believe I posted for basically to watch.
Made is thin and uniform in height. The powder can be pressed from one side by the upper punch. When that punch withdraws, a lower punch raises the part out of the die. The part is then ejected by the wiping action of the powder feed chute, which also wipes powder for the next piece into the die. Ejection from the press can also be accomplished using automated handling equipment. The density of pressed powder tends to decrease along part height as the distance between the compacting punch and die increases. To produce more uniform density, thick parts are compacted by a set of upper and lower punch.
Yep, so maybe another short video.
Lightly joined together. In this state, the parts have a so-called green strength, which is usually only sufficient for handling purposes.
So as you saw in this video, when they are in this green state, you can break it by hand. And another
lubricant.
video.
That mixture is put into a compaction press. We compact the shape into what's called a green part, and that will have a pretty low strength. Certainly enough to handle, but I always say it's like the strength of an aspirin tablet. You can, if you try hard, you can break an aspirin tablet. The structural properties, the end properties that you're looking for from the product are not going to be in that green part, but it begins with the shape. So the PEng process is kind of unique. You get a shape first, and then you get the properties. The properties are all developed in that sintering furnace. So for steel, we'll be in the 2000 Fahrenheit range, or about 1100 degrees Celsius range. Certain atmospheres are used. In the steel world, we use nitrogen as a protective atmosphere. Hydrogen is often used as a deoxidation or reducing atmosphere. Takes the oxides off all metal particles that have that oxide.
And you can watch the rest of course, the video if you haven't from one of those links that I sent you from YouTube. All right, so this is the process. Sometimes we need to do some secondary operation. Machining, of course, if we need to do, first of all, thread, making thread by powder metallurgy maybe is not a good way, and you learn more about it next lecture when we talk about forging. And you will see if we make thread by powder metallurgy, then thread are going to be very weak. Or sometimes when there is like side hole like that one, so you may need to do drilling afterward. So machining is some things, again, depends on the part that you are making by powder metallurgy. But obviously threading is something that needs to be done afterward. The second operation, which is very common, is impregnation. And sometimes people call it infiltration. So infiltration or impregnation, both are the same. And the process basically means that when you use powder, there is these porous or these extra spaces between particles. You want to fill it in with other things. In particular, you want to fill those available spaces with oil, with polymer, or with other metals. Depends on your application. If you fill it in with oil, it will call oil impregnation. If you fill it with polymer, it is called polymer impregnation, and let's say copper impregnation with other metals. So, but why do we do that? With oil, it's obvious when we want to create, let's say, journal bearings for gears. In fact, we are making a part which is self-lubricated. Polymers, if you, let's say, fill in those available space with polymer, now you're making a pressure-tight part, right? A part that is pressure-tight, which you may use for, let's say, a cap of some, or lid of some, let's say, vessel or something that you need a pressure-tight part. Let's see how this can be done. With oil impregnation, usually right after sintering, they basically dump these part, and they are still hot, into a bath of oil, and they leave it there for a day or 2 days. So they let the oil, and with the polymer the same, and polymer to soak in, basically. You can think of more like a sponge, so they get in. Other metals, it involves its own process, but they usually try to do it in the powder stage. Again, let's say the example of titanium and gold, you add that gold powder mixed with basically titanium. When you put it into a furnace, the lower temperature metal is going to melt and fill up all the gaps. So the oil impregnation, again, very common for self-lubricated gears. There are some applications which, like in robots, which the gear, the access is to the gear to lubricate is either difficult or it's not recommended to like add oil to it. So people use self-lubricated gear, and the bearing as well. Polymer impregnation as well, which I mentioned, and other metals is another example, which when you want to change the physical property of the part. Let's say you want a strong part, at the same time you want this part to have a very good electrical conductivity. So you use the other metal impregnation. And lastly is similar to other process. When you design something, you have to think ahead of time for manufacturing it, and you need to consider a few things. With powder metallurgy, things that you need to consider is the side hole you need to avoid. So these are the features to avoid. So one is the side hole, and second one is undercut. So do you know why we need to avoid these features?
Because you need to be able to mold it with well, easily from the top and bottom only, basically.
Exactly. So when you compress it into the mold, it's with undercut, and with the side hole, it's, as you mentioned, it's difficult to fill in the mold and compress it, right? You can think of, let's say, this one, if you compress it from the top, let's say you put it into a mold, let's say fix here, and you compress it from the top. So probably because this, you have the, like a void space here, this part is not going to, this section is not going to be compressed nicely. And the same with this part. And similar problem with undercut. So it sort of tells you that with powder metallurgy, you can think of the way that things are being compressed. You need to avoid feature that prevent this nice compression. So if all the layers are on top of each other compressed uniformly, then we are happy. If there is an undercut, like this one here, then you can think of, if you compress it from the top, then there is an area over here which is not going to be compressed, right? Not compressed. Another feature that we should avoid is this round corner. Always we like round corner, right? Remember, always we said fillet is a good thing, but there is one particular process which corner is bad. So avoid this. All right, now my pen has decided to stop this. And instead of that, so this is bad. This one is better. And similarly, you can think of why it is bad, and the second one is better is the way that you compress it. Like this one, as you get to the maybe outer layer, like you cannot really compress the powder. And lastly, this one, it can have an issue. You can think of why?
Thin wall?
Yep, thin wall. So avoid thin wall. Because again, when you compress it, first of all, thin wall, maybe it's easy to break when they are in a green stage, when you transfer it to furnace. But more importantly, when you compress it, maybe they don't get enough pressure to be compressed. So we try to make them as uniform as possible. All right. So I guess that's my last slide. As you saw, this process is relatively simple, popular, but simple, right? So you make powder out of metal. Hopefully now you learn how people make powder out of metal. So you melt metal, you pour it into a, let's say into a funnel or furnace, not furnace, sorry, the orifice, and you use pressure water to make powder. Or you use a turntable. You have the powder, you need to be careful with powder because it is explosive, and also handling it, is difficult. With powder, of course, people working around powder, they have to be careful for inhalation because powder, especially some metal, they are poisonous, or even for non-poisonous metal, still they are bad for people. So working with powder is not easy. So the process usually is automated. And you compress the part to the shape that you want. Usually we use this process for a smaller part, and for the part that we can make sure we can create a uniform layer by layer pressure. And we make a part, which we call it a green part. This part, then we move it to a furnace for sintering. And sintering, you learn, it's a process which is not melting, it's getting close to melting. Maybe I write it down here. Sintering. Temperature usually is around 70 to 90% of melting point. And also keep in mind, sintering is a long process. Sintering is time consuming. So can you guess how long it takes to sinter a part?
Hours?
Hours.
Days.
Days. Both answers are right. So sintering takes
weeks even.
I wouldn't say Josh, weeks, but it depends. Maybe for some part, you will see next week when we talk about additive manufacturing. Sometimes we do sintering, it may takes longer, but we say it takes hours. So it's not in a range of minute that you can think. For, let's say, some material such as copper or iron, it takes few hours. For some materials such as tungsten, you can think of a day or two. So it's a time-consuming process because you don't want to increase the temperature because everything is going to melt down. All right, that's all you need to know about powder process. Sorry, somebody had a question.
Yes, I have a question. Why does it take so long?
Again, because you don't want to increase the temperature. You want to like a slow cooking, right? If you increase the temperature, then the outer layer start melting. You don't want that. You slowly you want the temperature from the outer layer get into the core and then
Got
they
it.
bond together, right? Yeah.
Yeah, the slow cooking is a good example.
So you are from Greek, right? So you know the roast lamb. To make a good roast,
Oh yeah.
you need to let it cook slowly.
The slower it is, the better it tastes.
Exactly. So here, the slower the process is, we make sure a uniform heat transfer to all the parts and all the good bonding together. All right. So that's it, guys. Thursday, we will talk about another process, which is forging. And after learning about forging, then we are ready to move to a new process, relatively newer process, which is additive manufacturing next week. Okay.
I have another question.
Yes, please go ahead.
What happens to the oil that we add into the powder when we sinter it?
That's a good question. I wanted to leave this for the final exam. So now that you spoil it. So why do you think anybody can have an answer? What will happen to the oil that we added to the powder? Remember, in one step, we added oil to the powder. Where it was here, right? Step number 2. What will happen to that oil?
Yeah, evaporates.
Exactly, evaporate. So the oil evaporate, and that's why all the furnace, they have to have a good exhaustion system. And there are some research that people try to use water-based sort of lubricant, because oil, after it evaporates, of course, it's going to create maybe smoke, and they need to have some exhausting system. But yeah, it evaporates. All right. So that's it, guys, for tonight. See you all on Thursday.
Oh,
I have a question as well, if you don't mind.
Of course, Joshua, go ahead. One by one. I guess Joshua, go ahead.
Okay, I was wondering if there was a plastic analog to this process.
With plastic, next week when we talk about additive manufacturing, plastic powder is one way to make stuff, but it's more in the category of additive manufacturing. So is this your question? So if instead
yeah, that's basically my question.
Yeah. However, it's not, again, very common. With plastic, the main reason is because the conductivity is low, right? If you try to sinter it, again, some particles start melting, some nothing will happen because they are in the core. So there is a particular process, but it's not similar to that, which we use powder plastic, but with a different approach. Its process is mainly for metals.
That makes sense. Okay, thank you.
No problem. And somebody else also had a question.
Yeah. So I was wondering, you mentioned that sintering happens at about 70 to 90% of the melting temperature, and obviously there's a range around that. But you mentioned that it's possible to use this process with alloys of metals with highly different melting temperatures. So I'm just wondering whether if they're really different, whether the higher melting metal doesn't get a chance to bond just because the temperature isn't high enough.
Well, Jesse, you spoil another question for final exam. So let's see if somebody can answer this question and get a credit for it. So what Jesse is asking is a good question. It says, we go up to 70 to 90% of the melting point. Now imagine that you combine two powder. One is 1000 degree, another one is 500 degree. So which one we should go and what will happen to the bonding?
We'll use the cold one, because then the cold one will fuse the particles of the higher temperature metal together.
Good answer. So you get the credit. So Jesse, as Panos mentioned, when you have two different metals, different temperature, you your base for the furnace is the one which has a lower melting temperature. That one is going to be the binding basically source, right? So the other particle for the high temperature metal here is not going to basically do anything. They're just going to stay as they are. The lower melting particle is going to act as the binding. And sometimes even people, like the second metal, you can think of sometimes people use plastic. Like they use powder, plastic, and a metal. They mix them together, compress them, and then they put them in a furnace. The plastic melts and create that binding. It is cheaper to melt plastic, right? Does that make sense, Jesse?
Yeah, that makes sense. Thank you.
So let me then write it down here so I don't forget. With mixed powder of different melting point, we use the lower, how can I say, melted point as reference. Okay, so that's about it.
Will we need more time to sinter it if they're like that different in temperature?
The second one, let's say the higher temperature, we don't want it to be melted. The first one is acts as the binder. Right? If they are, let's say, close to each other, let's say you are mixing two things, which is 1000 C and 900 C, then there is a chance that the higher temperature also, the outer surface of particles get to that melting point and they fuse together. If there is like a huge difference, again, an extreme example is titanium and gold, then gold here, or let's say a metal, aluminum, and plastic powder. Then here the plastic is going to act as the binder and it's going to melt and fuse things together. So the aluminum is not going to be even touched. But in terms of times, no, of course, it depends on what material we use. But we don't want to get the higher temperature to act as a binder. Does that make sense, Ahmad, or no?
Yeah, it does. I was actually more questioning that if the temperature is, say, like one is 500 degrees Celsius and one is 1000,
right.
So we'll probably use something around 400.
That's right.
So will we need more time? Is it like we will need days to center it, or like it'll work fine if we just use few hours?
I don't know the exact number of 2 hours, but in terms of times, again, no, it doesn't make a huge difference because as long as we get to, let's say, 400 C in your example, and it creates the binding for that other one, we don't care about the other material with higher temperature to get too close to the melting point. You see what I mean? It's the lower temperature one that acts as the binder. We just care about getting that one to the melting point. So in terms of times, it may not make a huge difference. However, I don't have an accurate and exact answer for your question.
I think it would depend on the conductivity of the two materials.
That's also true. It's how fast the temperature can get to the core and the conductivity of the two.
All right, thank you.
Right. Okay. Any other question, guys?
Yeah, I've got one. You mentioned that this process can be used for gears and bearings, which, per my understanding, require fairly high tolerance and good surface finish. Does this process really provide that surface finish, or if we have a porous surface finish, do we have to machine it afterwards?
It provides that good surface finish.
Okay.
So Andrew, right?
Yeah.
So that's a good question. So this is one of those process which the surface finish is almost to the final shape that we want. Again, it depends on the application, but most of the case, the surface finish is just ready, is almost to the final stage, unless we want something, let's say those ring for piston that I showed you, which you want like a very smooth surface, which the secondary process is not going to be a lot of machining, maybe just a simple sanding, and then it will be done. But the surface finish is usually good. And even with the porosity that you mentioned, porosity sometimes first is something that we want because of oil lubrication. But if we don't want that porosity, that's why we have this extra step of adding polymer to it, like number B, polymer impregnation. So to remove any porosity, like this example, like you see, it shows sort of a porosity. But in this like gear or this bearing example, this porosity is something that we want. But the surface finish is usually smooth and ready to go.
Cool. All right. Thank you.
Do you have to consider the geometry creeping during the elevated temperatures that it's being sintered?
That's a good question, Philip. So Philip is asking when after sintering, after compressing it, and we send it to sinter, and there might be some geometry change. There is shrinkage, and that's why when people design something using powder metallurgy, they consider it and they have to compensate it for it during when they design the mold, basically.
Can I ask another question?
Sure. So Philip, does that answer your question before we get to Kutan question?
Yes, thank you.
All right.
I was wondering, is it any different with powder metallurgy parts or regular parts when like cracks propagate? Because there's theoretically, I'm guessing there's like gap between the particles and everything.
Yeah, that's a good question. So when we make something with forging, which again is the topic of our next lecture, there is a lower chance of crack propagation. With powder, of course, if there is especially a flaw during compression part or during sintering, maybe for some reason a region of a part is being defect and there is not a good binding, then there is a higher chance of basically crack propagation. So if we want to sort of rank them, so on Thursday you will see when we talk about forging. Forging is the best in terms of preventing crack or cracks. Casting is second. Powder metallurgy is second, and casting is the worst. Because in casting, there is a chance that maybe a region of a part doesn't solidify, or a region maybe solidify faster than the rest, and then there is a higher chance of crack propagation compared with powder.
Thank you.
Right. Is there any other question, guys? Are we good? Okay, seems you are good. So see you all on Thursday and have a great night.
Thank you.
Bye. See you later.
Thank you, Ahmad.